Hello everybody, this is the video for this morning. We couldn't connect because I finished my roaming data and Swisscom did a mess and now it's all blocked. So it will be blocked until today midnight, and as of April 1st I will get back my data, so it will work. Okay, but now also the upload of videos is very slow, so if you receive it in the afternoon, don't be surprised. I'm sorry about the situation. Okay, so the class that we should have had yesterday is about well, I will start with a reminder, then we will correct the exercises on page 20, and then we will continue with theory and exercises about potential energy and conservative and non-conservative forces. These exercises. Okay, so I did that computation. We take 4 joule, we divide it by the amount of joules in 1 kilowatt hour. So the units are joules over kilowatt hour. So it gives you kilowatt hours. Okay, and you get 1.1 times 10 to the minus 6 kilowatt hours. And so this you could write as 1.1 times 10 to the minus 3 watt hour, okay, because 10 to the minus 3 cancels with the 10 to the power 3, which is due to the small k here. And now you have 10 to the minus 3 watt hour, so you can say 1.1 milliwatt hour. Okay, we find this result, which is nicely compatible with the one in the book, except that in the book I guess they took a different mass. In the course they took a different mass for the book, so it gives a result which is slightly different, but it's the same order of magnitude, so we're happy. Good, now let's go to exercise 2. Exercise 2 is about 2 cars racing up a mountain pass. Okay, so this is exercise 2. We have a road which goes up to a mountain pass. The mountain pass is at an altitude of 2000 meters, so it could be the Simplon, for instance, and the start of the road is at an altitude of 550 meters. We consider, of course, I didn't mention it in the problem, we consider of course that there is no friction, otherwise all this changes. Or we consider that the 2 cars have the same friction, but let's just forget about friction, because friction always makes things more complicated. So what do we have? We have 2 cars, okay. Car 1, which has a power of 250 HP, and the other car 2, has a power of 180 HP. Okay, so the first thing we need to do if we want to compute something is to transform these units into watts, okay, because we need watts. These are the standard units for power. So how do we transform that? We saw that 1 horsepower is 746 watts, okay, and so here we will have 250 times 746, and down here we will have 180 times 746. So if you do the calculation, that's what you get, 186,500 watts. So we are going to write these powers in kilowatt now. The first one is going to be 146,5 kilowatt, and P2 is going to be 134,28 kilowatt. Okay, we are now in the right units to compute stuff. And now these are the powers, so these numbers tell us how many joules per second this these cars can produce. The first car can produce 186.5 kilojoules per second, and the second car can produce 134.28 kilojoules per second. Okay, so obviously this car will have more difficulty getting up to the top of the pass fast. It will take more time. And how do we estimate the time? As you know, the power is the energy divided by the time, or the work divided by the time. Anyhow, work is energy. And here, what is the work that we need to produce in order to get up to the path? This work is equal to the force times the distance. Now there is a small complication here, because the distance, it's not a straight line, this is a road. But if we consider that there is no friction, then going up this road in this way, and we will see it later, requires the same energy as going flat and then going up. Because when you are going flat, the gravitational force here does not work. Okay, the gravitational force is perpendicular to the motion at the same altitude. So here we don't do any work if there is no friction, and the work we will do is only the work which is needed to go vertically from down in the valley to the top of the pass. So this work is going to be the gravitational force times the distance. Okay, and there is an angle of 180 degrees, so this is going to be mg times the vertical distance. Okay, so this work here, I will write it is m times g times the distance. And so the mass, did we give the masses for the car? No, we didn't give the masses, so I'm sorry. Let's say that the mass of the first car is equal to the mass of the second car, and they both weight 2000 kilos, to make it simpler. Okay, so the first car, it will need, this is W1, this is F1, and this is M1. Okay, so it's going to be 2000 for the mass times 10, I will round up G to 10, times the distance, which is 2000 vertically minus 550. Okay, and the second car, okay, the second car, it has to do the same work, because it does exactly the same thing. It goes up from the valley to the top of the car. Okay, so now we need to invert this relationship here and say we need the time for the two. Okay, and we know that the power is the work divided by the time. This means that the power times the time is equal to the work. This means that the time is equal to the work divided by the power. This should make sense. Indeed, the work is the total energy we need to produce. The power is the rate at which energy is produced per second. Okay, the watts, the work is in joule, the power is in joule per second, which we call watts. So joules divided by joules per 7, this will give you seconds. Okay, so let's compute. The time for the first car is the total energy he's going to need. So I need to compute this first. Okay, it's 2000 times 10, so it's 20,000 times 2000 minus 550. Okay, and this gives us 29 times 10 to the 6 joules. So now the time for the first car is going to be the work. Anyhow, the work is the same for the two cars. divided by the power of the first car. Okay, so it's 29 times 10 to the 6 divided by the power of the first car, which was 186,500, and that gives us and that gives us 155.5 approximately seconds, right? And if I divide this by 60, this gives me about 2.59 minutes. Now what about the second car? It's obviously going to take more time because it's less powerful. Indeed, the time for the second car is the work divided by the power of the second car. So it's the same work, 29 times 10 to the 6 divided by 134,280, and this gives us, just a second, 29,000 million divided by 134,280. This gives us 215.97 seconds. So this is approximately, if I divide by 60, this is approximately 3.6 minutes. Okay, so you see, you have the same work to do. The work in the physical sense is to go up a mountain pass, and you have two different cars with two different powers. Of course, the car who has more power will be able to produce this work which is necessary in less time. Okay. Now we saw kinetic energy. Another extremely important type of energy is called potential energy, and we will say later that kinetic and potential energy summed up give something which is conserved, which is called mechanical energy. So let's now study potential energy. From the name you can understand kind of what it means. Okay, potential energy is contained in any system which has a certain configuration, and this system is therefore able to give you, to transform this potential energy into something else. Sorry. Okay, let me give you a few examples. Okay, let me use the camera. Okay, I have a calculator here. No, you don't see. Okay, let me do it here. You have a calculator on the table. If I lift it, I give it potential energy. I increase its potential energy, because if I drop it, it's going to fall and to produce a shock, and it's going to transform the potential energy into kinetic energy when it falls. Okay, and the higher this calculator goes, the bigger the potential energy that it contains. Okay, now I can give you a completely different example of potential energy. Take a capacitor. You remember from electricity, capacitor, two plates which are charged, they are connected to a generator. Okay, and so what happens? The negative pole of the generator is full of electrons. These electrons hate each other, and so they go here on the plates of the capacitor. A capacitor is a system of two metallic plates which do not touch each other. Okay, and inside the capacitor, as we saw, there is a constant electric field which goes from the plus plate to the minus plate. Okay, so one plate is charged positively, the other plate is charged negatively, and so there is an electric field inside from the plus towards the minus. And if you charge a system like that, okay, if you connect a capacitor to a power source, then the electrons will be pushed on that plate. The electrons will be removed from this plate, and so it will become positive. Okay, and now if you remove the generator and keep this capacitor in your hand, this capacitor contains a certain potential energy, because as soon as you connect it to a circuit, let's say now you connect the capacitor to a lamp which is here without any generator, well, the capacitor is going to discharge and it's going to produce an electric current inside the circuit, and it's going to make the lamp burn. So it's going to transfer energy to that lamp. Okay, so there are special ways to compute the potential energy for a capacitor. I don't want to do that. Another example, Ali, let's be creative today. Let's imagine you take a rat trap. Okay, rat trap, it's done how? I'm not a specialist of rat traps, but basically it's something like this. Okay, here you have a small hook. Here you have a strong ressort. Oh my God, I missed the word. Strong. Well, anyhow, you understood. And here you put a little piece of cheese. Okay. Now, when the mouse comes, sorry, my mouse is not very nice. When the mouse comes, what happens? The mouse is going to pull the cheese, and here there is something which is attached to the cheese. The mouse is going to move the cheese, going to try to eat it. This will move the hook. The hook will no longer hold, and this thing will close very suddenly and catch the mouse or even kill it, which is a very bad thing to do. Where's the potential energy here? Well, it's contained in the spring. Now the word came back. Okay, this spring here, it's quite a hard spring, and when you arm the trap, you take this piece of metal which was here and you pull it back and you attach it to the hook. In pulling it back, you have to give a force. Okay, it doesn't go by itself, and when you attach it to the hook, this spring here contains potential energy, and this potential energy, when you remove the hook, this potential energy is transformed into kinetic energy, and finally it's going to catch your mouse. Okay, so springs also have kinetic energy. Okay, if I take a spring which is not constrained, this is its natural length, it doesn't contain energy. Now if I make the spring longer, then it contains kinetic energy. Okay, by the way, this kinetic energy is 1/2 kx squared, where k is the constant of the spring and x is the distance between the rest position and the actual position of the spring. So you see, it's an expression that looks like kinetic energy. Okay, same thing if you compress the spring. This spring is going to want to expand, so it's ready to give you mechanical energy. So this spring contains potential energy. Okay, so potential energy is something very widely represented in nature, and the potential energy we are going to be interested in today is the one associated to objects in the gravitational field of the Earth. So I come back to my calculator. This calculator has a certain potential energy. If I lift it, it has more potential energy, because if I drop it, it's able to produce a shock, it's able to produce kinetic energy, heat during the shock, etc. And the higher I put it, the bigger the potential energy. So now we are going to derive an expression for that potential energy. So now, and here we have to use a convention. We have to make a decision about the size. The decision we make is the following: delta U is equal to minus W. This is the equation you see here. Okay, this equation is not extremely clear, so let's clarify it. Delta U is the potential energy, the final potential energy minus the initial potential energy. Okay, and this W, we saw it's mgd. Okay, so if I take a minus sign, this is going to be mgt, or better, because this is the usual way to say it, mgh, where h is the height. Okay, let's say this is the height of this motion, and now let's look at this. Imagine that the initial potential energy is 0. You will see later that this is a plausible hypothesis, because we can define the 0 of the potential energy wherever we want. Okay, if we set this to 0, then the potential energy which we get by raising the object by a certain altitude is certain altitude h is mgh. This is the formula for the potential energy of a mass which is in the gravitational field at a certain height h from the ground, or from some reference point you defined. Okay, you can also use this formula mgh for the two of them. Okay, you can also say that u final is mgh final, and that u initial is mgh initial. Okay, and now the delta u, the difference in potential energy, is going to be given by mg times the final height minus the initial height. So if you have defined the initial height here and the final height here, you see that this difference is just h, the distance from the floor. Okay, so please remember this definition of potential energy. Potential energy in the Earth's gravitational field is given by that. Of course, this is g Earth. Now if you go on the moon, you have to use g moon. So if you raise a mass by 1 meter on the moon, you are not going to give it as much potential energy as you would do on Earth. Okay, you are going to give it 6 times less potential energy, because the g on the moon is about 1/6 of the g on Earth. Okay, it's not obvious, but you will see that for applications it will be very clear, and we will get back to that. But now I'm following the structure of the course, and now the next point we need to treat, we will get back to that, to this equation. The next point we need to treat is conservative and non-conservative forces. I will not speak for 3 hours about that. I mean, conservative and non-conservative forces are a concept which is quite easy. You can read all that. I advise you to read all that. But basically, let me give you an example of one conservative force and one example of a non-conservative force. Okay? A very nice example of a conservative force is the gravitational force. Okay? And if you want to speak very nicely, you can say that the gravitational field is a conservative field. Why is that? Well, if I go from a point A to a point B, okay, I can go in different ways. Let's assume that this is the ground. Okay, we are in some landscape. This is the ground, and we want to take this object from here to here. Well, we can go different ways. We can go like this, straight. We can go like this. Okay, and we can go like this. Okay, and with every one of these motions there will be some work associated. So let's say this is path 1, this is path 2, this is path 3. Okay, what is the work on path 1? What is the work on path 2? What is the work on path 3? Let's start with the work on path 3. What do you think it is? If this height is h, okay, here we set h to be 0. Well, we saw it before in the exercise. This is also why I did the exercise before, talking about that. When we go from A to B, we can legitimately go flat, I mean horizontally, and then go up. Okay, and if I want to compute the work of the gravitational force, well, it's going to be 0 here, because displacement is perpendicular to the force, and it's going to be non-negative only here. So the work here, it's going to be mgh, or minus mgh if you want. For the situation 2, well, it turns out that if the field is conservative, then in the path 2, the increase in potential energy will also be mgh, and same for path 1. Path 1 may be more difficult to understand. Imagine, because we're going higher than the point B. But when we are going higher, we consume more energy, and when we come down, we get this energy back. Okay, so everything combined, the energy we need to go over this path is going to be the same as the energy we need to go over this path, which is going to be the same as the energy we need over this path. And so for doing calculations in all practical cases, we will use this path here, because it's much simpler to compute the energy on this path than on the other ones. Okay, so for a conservative force, work does not depend on the path followed from one point to another. Maybe this is not very clear for you yet, so it will become clear when I give you an example of a non-conservative force. Okay, let's imagine now we have these points A and B, but let's imagine these points are on my desk. Well, let me do them on my desk. Okay, I have point A here, and I have, where is it? And I have point B here. Okay, and let's suppose I want to go from point A to point B with my mouse. Okay, I'm pushing my mouse. Oh, okay, so I can push my mouse straight from point A to point B. I can push my mouse horizontally and then up to point B, and I can also do something completely crazy. I start moving my mouse in all directions until point B. Do you think the work is the same on these 3 trajectories? Let me write them down. Okay, on this trajectory, on this trajectory, and on this trajectory. Is the work going to be the same? What do you think? Think a bit. Of course, I mean, if you're smart, from the way I've been asking the question, you can understand that it's not going to be the same. Why is it not going to be the same? Because now the force which I'm considering is the friction force. Okay, so here I'm going in that direction, but my friction force is in the opposite direction to motion. Okay, so here there is an angle of 180, and on this, call it horizontal section, before we had no work with the gravitational force, but now the friction force does work, and it does produce negative work. Okay, and here too the friction force is now in this direction because it opposes motion, and the displacement is here. In other words, and it's the same on all this work. Okay, the friction force is opposite to motion, and motion is in the direction from A to B. And so the longer the path, the more energy you will need. Okay? Here, clearly, the work depends on the length of the path, because the work is always the product of FF and D is always the same, and the angle is always 180 degrees. So the longer the path, the more energy you need. And so in this case, this path, and this path do not require the same work. If we call them 1, 2, 3 like before, the work for following path 1 is much bigger than the work for following path 3, which is longer, which is bigger than the work that you need to follow path 2. Okay, so here work does depend on the path, and so this field, this force field, is non-conservative, and the force we are talking about here is the friction force. Okay, the friction force is never conservative. The friction force always makes you lose energy. Well, always transforms your kinetic energy into heat, right? A conservative force field is a field in which the work from going from a point A to a point B does not depend on the path chosen. A non-conservative force field is a force field in which work does depend on the path follows. So the best examples for here are the gravitational field. I already said it, but there is an other example, which is the electrostatic field. Okay, you imagine, let's go back to the example of the capacitor that we discussed before. We have a capacitor, we have plus charges on one side, minus charges on the other side. Inside the capacitor we have a uniform electric field. We have a point A here, we have a point B here, and whether we go from A to B following this path, or this path, or this path, or this path, well, I should not get out of the capacitor. Okay. It's going to be the same. The energy needed is going to be the same. Whereas here the main example is friction. Friction is a force that degrades energy. It degrades, for instance, kinetic energy into heat. Heat is the most degraded form of energy. Okay? And so when we do physical work, we try to work with a conservative force, because it's much nicer to work with a conservative force. It's much more interesting. We generally try to avoid friction, but sometimes it cannot be avoided. Voila! This was for the chapter of conservative forces. So I didn't lie to you. Okay, this is what I told you. The work done by a conservative force on a particle moving between 2 points does not depend on the path taken by the particle. And this also means, this is a consequence of that, okay, that the net work done by a conservative force on a particle moving around any closed path is 0. Why is that? Let's say you have a point A, you have a point B, you choose one path for going from A to B, okay, and this has a certain energy, this takes a certain energy, this takes some work, WAB. Now if I come back to point A, the forces will be in the opposite directions, and so this will be minus WAB. Okay, so this work is going to compensate this work, and on a closed loop the sum of the work will be 0, and so the total work will be 0 on a closed path A to B back to A. You don't get that? Let me explain you better. We have a gravitational field. Okay, so the have gravitational field, I will draw it like that. I will draw field lines just like the electrical field. Okay, this is the gravitational field. Okay, and I go from point A to point B. I will choose the simplest path, which is the path that goes horizontally and then up. Okay, so here the gravitational force is directed downwards. Here we don't do work. Here work is 0. Here we go up. So here we do work, which is mgh, where h is the height here between the level of point A and the level of point B in the gravitational field. Okay, this is the work, so let's be precise. The work done by the gravitational force is minus mgh, because the gravitational force is pointing down and h is pointing up. Okay, now let's go down. You want to follow the same path or another one? It's the same. Okay, let's use another path. Let's use this path here to go back down. Okay, here we are going to have 0 work because the gravitational force is perpendicular to the displacement, but down here we will have work, and now the displacement is downwards, the force is downwards, so this displacement here, the work of the gravitational force on this displacement will be positive. So here we will have omega g is equal to plus mgh. And now if you sum this wg with this wg, they have opposite sides, and so the total work for going from A back to A is 0. Okay, I took the green path because I didn't want to put the path at the same place as the other one, but you can exactly in the same way choose, come back via the same path, and you will see that since the displacement is in the other direction, it changes the sign of the work. Okay, good. Now let's do a little problem, and it's a problem which will require you to think a bit. I let you think about that. I will go have a coffee and we meet in 3 minutes when you have done it. Okay, try to do it. Okay, maybe you have a solution. So let me restate this problem. We have a point A, we have a point B, okay, and the work necessary to go from A to B over different paths, or B to A, we have to see that, is indicated here. So we have one path which goes about this way, okay, and here the work is 60 joule. In the statement they tell you that there is one single force which is acting. So let's suppose that this force is going in this direction, for instance. Okay, it could be in any direction, but this force vector is going to be in the same direction all over the area. In other words, there is a force field which is like this, okay, and this force field has the direction, has a constant direction. Okay, so here we have 60 joules. Fine. Now when we come back, we have 60 joule again. Do you like that? Does it look conservative? Okay, you know that the work from A to A over a closed loop should be 0 if the force is conservative. Is it 0 here? No, it's not 0. Here it's 60 plus 60, which is 120. Okay, so this force is obviously non-conservative, and it could very well be a friction force, for instance. Well, yeah, it could be, okay, because you take as much energy to go there that you take to come back. And then you have another path which is going somehow like this. It's going from A to B, and now you have minus 60 joule. So from A to B you have 60 joule here, and again from A to B you have minus 60. It's not possible. If this were a conservative force field, then independently of the path chosen, it would require the same amount of work. So this force field is clearly non-conservative. Okay, now let's maybe play another game and see what kind of values we should give to make this conservative. Okay, I'm now putting in green the values for a conservative force field. Let's keep this one, 60 joule. The work for coming back should be minus 60 joule, and the work for another path from A to B should be also 60 joules, and this would be a conservative force field. Now we have another very basic exercise to do, but it's important. Okay, we have a 2 kilogram block of slippery cheese. Yeah, it's this book. Okay, they always take strange examples, but it's nicer than saying a mass. Okay, so a 2 kilo block of slippery cheese, it slides along a frictionless track. This is very important. Okay, if there was friction, it would never be conservative. So it's frictionless from point A, which is here, to point B, which is here. Okay, it's going down that way, going back up and ending up in B. So the total distance here is 2 meters, and the vertical distance here is 80 centimeters. How much work is done on the cheese by the gravitational force during the slide? Please try to compute it and come back for the correction in a minute. Okay, so let's compute it. What's the line of reasoning here? Okay, it's a gravitational force acting and there is no friction. So this is clearly a conservative field. If it's a conservative field, it means the work is independent of the path chosen. Aha, it's independent of the path chosen. If it's independent, then choose the easiest path. Okay, and what's the easiest path to compute the work? It's this one, horizontal and then vertical. And on the horizontal path, the gravitational force is perpendicular, so here the work is 0, and here the work is going to be the work of the gravitational force. Okay, and the gravitational force acts downwards. The displacement vector is here, it is directed downwards, so the angle is 0. So now we can compute the work of the gravitational force. The work of the gravitational force is the gravitational force scalar product with the distance. So it's the intensity of the gravitational force times the length of the distance times the cosine of the angle, but the angle between the two is 0, so this is 1, and Fg is the m times g, and so the work of the gravitational force is mgd. Okay, and so you can compute it immediately. It's 2 kilograms times 981 times the distance, which is 0.8 centimeters. So this is going to be about 2 times 10, let's say, which is 20, times 0.8, 20 times 0.8 is 16 joule. Is that correct? Yes, 16 joule. And this is independent of the path chosen. Okay, now let's get to the last theoretical section. I told you already about that. Okay, you remember we had delta U is equal to minus the work of the gravitational force, and this now you can express it in this way. okay, the delta U, the final potential energy minus the initial energy, is mg times the final height minus the initial height. So mgyf is uf, mgyi is ui, this minus sign comes here, and so you can express that as mg times the difference in height. In other words, mg times the height you are moving vertically. Okay, and so we get to the final formula. If we decide that the initial potential energy is 0, because we always have the right to set a reference level for the potential energy. See, if we say that the initial potential energy is 0 at y is equal to 0, then yf is going to be h, and finally we get this formula, which is the final formula for the potential mechanical energy. Okay, this one I will leave it aside for the moment. I recall you the elastic potential energy. I told you before, I'm not going to demonstrate this, but the potential energy for a spring is 1/2 kx squared, where k is the spring constant and x is the distance between the actual length of the spring and the length of the spring where it's not compressed or made longer. Good. Now there is a nice exercise on the next page. I would love you to do that for next time. So let's say you will do this homework for the next time, which is going to be the 7th of March. You have the correction here. Try not to look at it and just to reason with this formula for the potential energy mgh. And here in this exercise you will have to set the 0 of the potential energy in different places and to compute the potential energy as a function of that 0 level. Okay, I'll let you do that for next week. I wish you a nice end of the day, end of the week. I am sorry for my connection problems. It will be fixed as of tomorrow because a new month is starting, so we'll have again my 100 gigs for connecting. Thank you very much. Be good, boys and girls. Be strong, and see you sometime in the future. Bye bye.